So we have been in module 2, and in module 2, we were learning about root finding for nonlinear equations. And we have gone through the bisection method, Newton's method, secant method, one-point iteration methods, numerical evaluation of multiple roots. I'm going to finish up roots of polynomials, and we did miss one day. So I'm going to leave you guys to do Aiken's, Euler's, and Horner's method on your own. And then we'll come back to that if you guys have some questions. Okay, so we were right at the very end of looking at the roots of polynomials and how to get a handle on what type of polynomials we might actually, what kind of roots we might actually have for a polynomial. So the first thing we had looked at was, we looked at locating some of the roots using the fundamental theorem of algebra. We looked at bounding some of the roots using Descartes' rule of signs. I gave you an example where we were able to look at the number of positive roots, and then in order to find the number of negative roots, we look for the number of positive roots of p of minus x. So from the last example, we were able to show that the polynomial either has one of two possibilities, because it has one negative root and 0 or 2 positive real roots. So therefore it has the one negative root. It could have 2 positive real roots and 2 complex roots. I don't know how that says 4 and 4. That should say 4 and 5. That's the 5th root. And then we have, it could have no positive roots, 0 positive roots, and all the other roots are complex. Okay, so we also want to look at one other thing that is a upper bound for all the roots of p of x. And we're going to attribute this fine fact to Cauchy. All right, so given zi as a root of p of x, and again, p of x was a n x to the n plus dot, 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 all the way down to a1x plus a naught. We can get that the absolute value of any root, and that could actually mean the modulus if the root is complex, is less than or equal to 1 plus the max over 0 less than or equal to I all the way up to n minus 1 of the absolute value of AI over AN. Okay. So an example of that is P of X. This is the same one we were looking at, x to the 5 minus 2x squared minus 3x plus 1. So we have AN is 1, and then the max over 0 less than or equal to I less than or equal to n minus 1 of the AIs is equal to 3. So that implies the absolute value of ZI is less than or equal to 1 plus 3, which is equal to 4. Okay, so now we have several things that we know about this polynomial. Okay, so we have an idea of the positive real roots, whether it has 0 or 2. We have an idea of the number of negative real roots, it's only 1. And we also know that of the real roots that it has, that the upper bound for all the real roots is that the modulus has to be less than 4. Okay, so for the real roots then, so all the real roots are between -4 and 4. Okay, so that gives you a starting point. So the above techniques provide a starting point. When choosing x0 or x0 and x1 for your numerical method. Okay, any questions about that? Again, we can always graph it. Graphing sometimes helps. All right, gives you a starting point for where it is. Okay, so what we have left, I think I wrote it down. So we have left G, Aitken's method. Okay, so Aitken's method is a technique to accelerate the convergence. Then we have Muller's method. I think I have that spelled wrong. And Muller's method is helpful for finding complex roots. And then I is Horner's method. And this is a method to evaluate a polynomial in a nested manner. Okay, so I'd like you guys to look over those. If you have any questions, let me know. There are certain things we have to cover. And so I need to move on.